Imagine building this lightning fast, perfectly functioning application in Python. Like you're leveraging thousands of GPU cores, it's doing massive parallel computations with absolute ease.
Right, living the dream.
Exactly, living the dream. And then voluntarily deciding to just throw the entire thing in the trash.
Which is wild.
It is. But welcome to the deep dive, everyone. Today we are looking at a set of developer notes from the year 2026 by an author going by the handle Luck036, who did exactly that. We're tracing this whole journey of taking a GPU-accelerated algorithm and completely rewriting it in Rust.
Yeah, they were chasing the ultimate holy grail of software engineering, which is zero-cost compile time safety.
Right, and it's such a relatable mission for anyone who builds software. Okay, let's unpack this, because before we can even dissect the language choices or dive into Rust compile time guarantees, we have to look at the mathematical problem dictating the hardware choices.
Yeah, you have to understand the math first. The notes focus on this thing called Pitt's randomized vertex cover.
Right, and for those who haven't looked at graph theory lately, a vertex cover is basically a set of points in a graph that manages to touch every single connecting line or edge. The goal is to find the absolute smallest, cheapest number of points required to touch everything.
And doing that mathematically, like finding the perfect minimum cover for a massive, complex graph, is computationally brutal. It scales terribly.
Which just takes forever, right?
Exactly. So Pitt's algorithm doesn't even try to find perfection. It uses this two approximation approach. It basically guarantees mathematically that the answer it finds will be, at worst, twice as expensive as the perfect theoretical answer.
Which gives you this highly bounded, very safe worst-case scenario. And looking at the notes, the way it actually gets there is probabilistic.
Yeah, it uses loaded dice, essentially.
Right. For any uncovered edge, it looks at the two endpoints and picks one based on probability that is inversely proportional to its weight. So the lighter or cheaper vertices have the dice heavily loaded in their favor.
And that loaded dice mechanic is the key to the whole operation. Because it relies on probability rather than, fixed sequential logic, a single run of the algorithm might give you an okay answer or a pretty mediocre one.
Right, so you don't just run it once.
Exactly. To get a truly optimized result, the developer employs a Monte Carlo approach. You execute this randomized algorithm independently, say, nuller trials.
So it's like trying to efficiently staff a network of checkpoints. You assign the lighter or cheaper resources first, but instead of just doing it once and hoping for the best, you simulate the staffing plan thousands of times in parallel.
Yeah, and then once all those trials finish, you just scan the results and pull out the absolute lowest cost cover overall. The higher your nuller, the more trials you run, the closer you get to optimal.
The closer to perfect you get. Which means the simulation needs to run thousands of times. And if a CPU is like a high-speed, incredibly complex robotic assembly line capable of building one highly sophisticated car at a time.
We definitely don't need that here.
Right, we don't. We need a GPU, which is essentially a massive grid of 10,000 stamping presses, just stamping out identical basic middle washers simultaneously. Every single Monte Carlo trial is completely independent.
It's trivially parallel. That's a great way to frame the hardware match, by the way. The GPU provides the stamping presses, and the developer applied this brilliant optimization trick to make sure those presses just never run out of raw material.
The bitmask trick.
Yeah, the bitmask trick. Because instead of passing around complex objects or array structures to track which vertices are currently in the cover, they compress the entire state map into a bitmask.
So they literally cram 32 individual vertices into a single standard EAR32 word.
Right. And what's fascinating here is the cascading effect of that one optimization. Because in GPU programming, your biggest enemy isn't computation speed.
It's memory bandwidth.
Exactly. Waiting for data to travel from the main VRAM to the processing cores takes an absolute eternity in clock cycles.
Just sitting there waiting.
Yeah. But by compressing the entire vertex state down to a 32-bit integer, the entire cover state for a small graph fits perfectly right into the GPU's L1 cache.
Which is the ultra-fast memory physically resting on the processing chip itself.
Right, it's insanely fast.
So the math is simple, the hardware match is perfect, and the memory footprint is microscopic. But mapping independent mathematical trials to thousands of hardware cores isn't something you just write from scratch in C++ on a Tuesday.
No, absolutely not.
You have to prove the concept first. And that means reaching for the ultimate prototyping sketchpad.
Python.
Python.
Specifically Python using the Numba CUDA library. because this allows you to prototype highly complex parallel algorithms without constantly wrestling with memory pointers or writing tons of boilerplate C code.
Yeah, the notes describe the Python implementation as basically magic. You write your standard Python function, and you literally just type the decorator at CUDA.jit right above it.
Just one line of code.
Right. And under the hood, Numba automatically translates your Python abstract syntax tree into machine code and then directly into PTX.
Which is the specific instruction set that NVIDIA hardware natively reads. It's brilliant.
And your standard NumPy arrays just seamlessly map over to CUDA memory pointers.
It is an incredibly powerful abstraction. You get the iteration speed of Python with the execution speed of raw silicon.
Wait, I have to push back on this a little bit because the notes call it zero boilerplate. Yet the developer is relying on this massive Numba library to do all the heavy lifting. If Python is this easy, why on earth would anyone abandon it to rewrite the whole thing in Rust?
That is the big question. And what's fascinating here is that you've hit on the exact reason the developer initiated the rewrite. Abstraction is a double-edged sword.
Right.
Python is phenomenal for proving that the math works, but when you deploy that code into a production environment where you, as the developer, do not control the state of the user's machine.
Oh, right.
Yeah, Python exposes severe structural fragilities.
The dreaded dependency hell. Like,
Mhm.
if the underlying CUDA toolkit version shifts on the host machine or the user updates their Python environment, doesn't that whole magical abstraction layer just immediately shatter?
It absolutely shatters, and that's just the start. The notes lay out several critical limits. First is the Python Global Interpreter Lock, or the GIL.
Ah, the GIL.
Yeah. Even though your GPU is running thousands of concurrent threads, the host-side Python code orchestrating that GPU is forced into a single-lane highway. The GIL ensures only one thread executes Python bytecode at a time.
Which creates a huge bottleneck when you're trying to feed massive amounts of data to the graphics card.
Right, exactly. And because Python is dynamically typed, you completely lack compile time safety.
Right, hello runtime bugs.
Yeah.
You could accidentally pass a floating point number into a function expecting a strict integer.
And the code will happily accept it, right up until the very moment it tries to execute the math on the GPU, at which point it just throws an exception and dies. But the most glaring issue the developer noted was gracefully handling hardware absence scripts. If you deploy that Python script to a machine that simply doesn't have an NVIDIA GPU, it doesn't try to adapt. It just throws a hard runtime error and terminates.
It just gives up. So because Python hits that structural ceiling in production, the developer goes looking for a steel foundation. They turn to Rust to chase the zero-cost holy grail.
Yeah, getting that raw, unadulterated GPU performance without sacrificing rigorous compile time checks.
But Rust doesn't natively speak to NVIDIA hardware. It requires a bridge.
And building that bridge is where the architecture of this project gets genuinely brilliant. The developer utilized a Rust crate called CUDA, specifically version 0.12.
Okay, here's where it gets really interesting. Because usually, if you want a system-level language to talk to a GPU, you have to write your GPU kernels in a completely separate C++ file, use NVIDIA's heavy NDCC compiler to build it, and then somehow link it all together in your build script.
Right, the traditional way is a massive headache.
But the developer didn't do that here. They literally took the raw CUDAC kernel code and embedded it straight into the Rust file as a text string. An Enster literal.
I know, it sounds chaotic, putting raw C code inside quotes within a Rust file. But the mechanism behind it is remarkably elegant.
How does that even work?
Well, the CUDA library leverages a technology called NVRTC, which stands for NVIDIA Runtime Compilation. When your Rust program actually boots up, it takes that string of text, links it against the CUDA driver API locally, and compiles it into machine code right there on the fly.
So it completely eliminates the need for an external C++ build pipeline. You don't need NVCC installed. You don't need separate directories for your GPU files.
Nope. Everything is self-contained inside the single Rust binary.
That is wild.
And because it's built in Rust, the developer could systematically solve the Python crash problem using Rust's robust error handling. They engineered this brilliant three-tier fallback system to guarantee the mathematical trials always complete.
Yeah, this is the part that really grounds the architecture. Think of it like a freight logistics network or even an airplane's redundancy systems.
I like the airplane analogy.
Yeah. So tier 1 is your ideal state, the hyperdrive jet engines. If the Rust binary is compiled with the CUDA feature flag enabled and it detects a compatible NVIDIA GPU on the machine, It routes all the trials through those hyperdrives,
But if those jet engines fail, say the machine has no GPU, or the CUDA drivers are corrupted, or you just forgot to install them
which happens all the time.
all the time, the software dynamically downgrades to tier 2. It intercepts the error, bypasses the runtime error that killed Python, and switches to CPU Rayon.
And Rayon is Rust's data parallelism library, right?
Exactly. It utilizes every available core on your CPU to run the trials concurrently.
So it gracefully falls back to turboprops. It's not as fast as the jet engines, but it's still moving a massive amount of cargo in parallel.
Right. And then if the user is running a tiny graph or explicitly wants to run a pure bare bones execution,
That triggers Tier 3, the CPU sequential fallback. It executes the trials one by one on a single CPU thread.
the trusty glider mechanism. It's slower, but it's guaranteed to arrive.
It never just falls out of the sky like the Python script would. It actively diagnoses its environment and routes the workload accordingly.
But, building that hyper resilient aircraft from scratch forces you to deal with the physical realities of the terrain. The notes are incredibly transparent about the friction of moving from Python's magical abstraction into Rust's explicit, exacting environment.
Oh yeah, let's look at the
Mhm.
trenches.
Yep.
Because the profiling alone sounds like an absolute nightmare. How do you even verify that your embedded text string is actually executing math on the physical graphics card?
Well, profiling GPU code requires specialized tools, and the developer noted a major shift in the ecosystem here. If you look up countless tutorials online, they'll instruct you to use NVProf to measure your kernels.
Right.
But if you are working in a modern environment, specifically CDA12, NVProf is deprecated. It's essentially a dead stub.
You'll just be shouting into the void wondering why nothing is working.
Exactly. You have to migrate to the modern suite. So you need an on-site compute to verify the mathematical execution of the kernel itself, and NSYS and site systems to trace the exact timeline of when data is traveling across the PCIe bus between the CPU and the GPU.
But even with the right modern tools, the hardware doesn't just willingly hand over its telemetry. The notes detail a specific Windows bug they hit, the ERNVG, Priestier Permer error.
Oh, yeah, that one is a pain. It's a fundamental security block. By default, the Windows operating system will actively block third-party software, even legitimate diagnostic profilers, from reading the raw hardware performance counters on the GPU.
So how do they get around it?
To fix it, you have to manually dive into the NVIDIA control panel and grant an explicit permission override. It's exactly the kind of obscure one-time environmental friction that can stall a deployment for hours if you don't know what you're looking for.
And once you get the profiler working, you have to fight the dependency manager. Because in the Python setup, you worried about version mismatch causing silent failures. In Rust, you have the versioning panic. Look at how strict CUDA version 0.12 is.
This raises such an important question about how system-level languages enforce stability. In Rust, you manage dependencies in a file called cargo.tomwall, and CUDA completely refuses to guess what hardware you are running.
It demands to know everything up front.
Yes. If your machine has CDA version 12.3 installed, you must explicitly declare the feature flag CUDA 2030 in your cargo file.
And if you just type CUDA 12, or if you forget the flag entirely.
The compiler actively panics and halts the build. It enforces absolute precision. It demands to know the exact architectural target before it will output a single line of binary.
Wow. It's compile time safety really showing its teeth. It's forcing you to map the environment perfectly. And that same strictness applies to the physical memory, right? We talked earlier about passing data. You can't just take a standard Rust reference like an NI32 and feed it into the GPU kernel.
Right, because the compiler knows the physical layout of the machine. The CPU and the GPU have physically segregated memory pools. The GPU literally cannot see the memory addresses managed by the CPU.
So if you try to pass a standard Rust reference,
The compiler immediately stops you with a device repr not satisfied error.
it's like giving the GPU a map to a house it isn't allowed to drive to.
Exactly. To cross that PCIe bus, you have to physically copy the data over. For simple scalars, you pass the data by value. But for larger collections, CUDA forces you to use explicit types that mirror Rust's concepts but live entirely on the graphics card.
So you use like a CUDA slice to represent an owned mutable block of GPU memory.
Right, it's basically the GPU equivalent of Rust's VEC. Or you use a CUDA view if the GPU only needs read access, like an immutable slice. Every single byte of data requires the developer to explicitly state where it physically lives and who is allowed to modify it.
So what does this all mean? The developer battles through deprecated profiling tools, obscure Windows security blocks, strict version panics, and hyper-explicit memory mapping. They give up all the seamless magic of Python decorators. What is the ultimate payoff for enduring all that friction?
The payoff is absolute certainty.
Which is huge.
It is. The notes confirm that the Rust port achieved 100% feature parity with the Python original. But unlike the prototype, this architecture is verified by 194 automated tests.
Wow, 194.
Yeah, and 6 of those are explicitly designed to test the pit kernel execution right on the hardware.
And with the diagnostic logging they implemented, you can monitor the terminal and see definitive, auditable proof that the workload routed to the GPU path successfully. They hit the exact goal they set out for. Rust plus CUDA equals zero-cost GPU acceleration with compile time safety.
And because they built on such a solid foundation, the path to scaling is incredibly clear now. The notes outline specific future optimizations, like right now the algorithm utilizes 64 threads per block.
Which the notes admit was just an arbitrary choice to get the kernel functioning,
All
right?
right, just a starting point. But in GPU architecture, threads are grouped into physical hardware units called warps, which are usually 32 threads wide.
Okay.
So by setting it to 64, they are guaranteeing 2 full warps per block, ensuring no idle cores within a warp.
Okay.
But by deeply tuning that block size against the graph dimensions, they can maximize hardware occupancy.
That makes a lot of sense.
They also outline a plan to move frequently accessed vertex weights out of the L1 cache and into shared memory, which is a user-managed space on the GPU that is even faster.
So they're moving from just making it work to squeezing every single nanosecond of performance out of the silicon.
Exactly. And eventually, they even want to implement multi-GPU support, coordinating multiple cards to run massive graph approximations concurrently.
If we connect this to the bigger picture for you listening, this deeply technical devlog is a perfect microcosm of a massive shift occurring across software engineering today. If you've ever dealt with a deployment that crashed in production just because a minor library updated overnight, you understand why this developer abandoned Python.
For sure. The industry is aggressively moving away from relying on duct-taped prototype scripts to handle heavy computational workloads.
It really is.
We are entering an era of precision engineering, where robust, type-safe architectures force you to solve errors at compile time. It guarantees that when the system actually deploys, it processes data relentlessly without ever breaking down.
You do the hard work up front so you can sleep soundly when the code is running in production.
Which leaves us with a truly wild final thought to ponder.
Yeah, this is the part that bends my mind a little bit.
Right. We just spent this time discussing how a developer literally embedded raw C code inside a Rust program, just as a simple text string, and allowed a runtime compiler to translate it for a completely different piece of physical hardware on the fly.
As compiler technologies like NVRTC get smarter, more dynamic, and deeply integrated into our primary languages, are we heading toward a future of language-agnostic superbinaries?
It really makes you wonder.
Just imagine a world where the code you write is nothing more than an abstract mathematical intention, and the machine itself autonomously decides, microsecond by microsecond, whether to compile that intention for a standard CPU, a parallel GPU array, or maybe even a specialized quantum coprocessor.
It completely blurs the line between the language you type on your keyboard and the physical hardware executing the logic.
It really does. Something to mull over. Thank you for taking this deep dive into the 2026 Dev Notes with us. Keep exploring the bleeding edge, and we'll catch you on the next one.